So we'll be starting off with this. Let's see what it is. So first question is, what do you understand by this? Code fast or fast code? Any difference? Or yeah, you're saying something. Okay, so if I told you to code fast, what would you do? Okay, fine. And when I ask you to write a fast code, like, yeah. So basically, this table summarizes. So on more of COMC side, you have got C++, Java, and the faster way, like faster code that you can write is in C or assembly. Same in microcontroller side, you have got Arduino. Here you have got embedded C. We'll talk about it later. And both of them have their own pros and cons. So last minute submission, you need Arduino. But if you want to make something which is commercial, which is like robust, you'll have to go for embedded C. And yeah, so and that star over there is because this. So all this time there are two things that you'll have to take care of. Like whenever you are comparing something, it's always assumed that your programmer knows stuff. Okay, it's not some random person who's put write a hello world program. And the second thing is compiler. So optimization depends on how good or bad your compiler is. So from platform to platform, your degree of optimization changes. Okay. So I have an example over here. This is a code written by one of your fellow mate, and I don't know if you can guess what it is. Somebody guess? Yeah, something like that. Yeah, piano. So this is written using only Arduino, like all the Arduino commands, right? Serial.write, serial.begin, all the good looking commands and stuff. So when you compile it, you take like 2608 bytes of memory, that is 8% of program storage, and 194 bytes of dynamic memory, that's your RAM. Okay. Now the same code, like functionally the same code, has been written in a primitive language. Okay. So yeah, here you won't find any good looking code as such. There's some random registers and stuff. Even I don't remember what it is, but now you take like 786 bytes of program storage and 30 bytes of memory, and it does functionally the exact same thing that code does. Okay, so like why did it become so efficient? Okay, thing is, compilers cannot match humans. That is, a good programmer can write a code which is way more efficient than like using a higher level language that compiler compiles into lower level language. Okay, so that is one thing. And so like with every high level language, there's something called fail safes. So you kind of keep on checking like different functions do not interfere with each other. So those extra lines of code, maybe there's no interference, right? So those extra lines of code are basically redundant. You know that there's no interference, still those will be executed, compiled, and it's like adding to your program space, taking more clock cycles and stuff. So yeah, the example is Arduino ka analog read. So problem with analog read is when you do this analog read A0, what it will do is call the function. In the function it will say that okay, I want A0 channel. Then in A0 channel it will check if it's an output or input. So there's like a lot of checking going on if there should be an actual analog read that should be happening, right? So that's like waste. I mean, if you know that you are taking analog samples like far apart using only A0 and not any other channel, not any other pin, there's no use of having all those redundancies, right? So you can just clip all of that and have only the bare minimum code that's required for an analog read. Okay, so that is somewhere you can like save a lot on clock cycles and program space. Okay, and programmer can exploit the hardware because you being the programmer know what your end application is, right? You know what all results are required, what you can discard, but the compiler doesn't really know. So it follows same set of rules, right, for compiling a high level language or high level code to a low level code. So if you can, the entire point being, if you go down the hierarchy of coding, you can write more efficient codes. Okay. Now Okay, how to code efficiently. So first thing is code in assembly. Go bare minimum, like every register would be manipulated as you wish. It's like there's basically nothing a microcontroller or a compiler is hiding from you. You know what all is going on like inside your code. So at any point if someone asks like what in which state the controller is, you can like pinpoint to the state or to whatever line your assembly program is being executed, right? So that is like kind of the most efficient way of writing code, provided you know like you are good at assembly and you know how exactly the controller works. So that is one thing. But because assembly language is kind of platform specific, I mean, okay, there are some standard commands and functions, but still it's not, you know, like universal. Different platforms won't support like specific operations like multiplication. Okay, nowadays it's available in most controllers, but earlier it wasn't there. So you would not want to like learn assembly code for one family, and then when you are given another controller, you won't want to learn the entire stuff again, right? It's too much of work. So take a step back. Code in C. So embedded C is because it follows some kind of standard. Okay, no, again the registers will be different and stuff, but your algorithm like for loops, if conditions, while loops, jump statements, they are basically same across the platform. So yeah, it's like learn it once, and for specific platforms you'll need to learn only like small bits of code. Okay, so it's very easy to port code for like across the platform. Okay, architectural and logical exploits, we'll talk about it, but they're like really interesting to speed up your code, especially when you want to do real-time coding, like input and outputs are like coming at a high speed, or you want to process them really fast. You might consider using them. Okay, now the platform and its limitations. So like an Intel i7 is different and an Atmega 1328P is different, right? You cannot expect GTA 4 to run on your Arduino. So just know the limitations of your platform and code accordingly, that what is kind of heavy for the controller or for your embedded system, and what is like can be done like very easily on your controller. We'll also look in detail about that. Algorithm optimization is based on more of how good your algorithm is. It has less to do with your hardware and more to do with how good you are at programming. Okay, and free the ALU. Okay, so most controllers have just one arithmetic and logic unit. So the more you shift work from ALU to other peripherals, okay, I shouldn't use the word right now, but something like that. So the more the ALU is free, you have like, you can push in more instructions that actually make sense. Okay, so don't let the ALU do redundant work or something which is like very simple. For example, I++, it's like adding 1 to a number, which is like very simple. But if you want the ALU to do that, it's going to be, I mean, instead of that you could have done a multiplication or something which is way more sophisticated, right? So that is also something we'll look at. Yeah.
No, but I have to perform that I++, not the
You can do anywhere else. You can use a timer. If you are sure that my for loop is going to execute in 13 microseconds, I can use the timer register as my I and do I++. Okay. Assembly coding. Okay, so as I told that you can manipulate individual instruction, like every single bit in the microcontroller is under your control if you go for assembly coding. So yeah, it's like you have the control of hardware, like what all hardware components should be doing what all tasks is like directly under your control. So yeah, basically the same thing. Avoids redundancies and flexibility to write bare minimum code. Now avoiding redundancies, again, the programmer should be good enough for that. Okay, he should know like what all tasks are not required at all. Like so in assembly, or if you refer datasheet of any microcontroller, you will see that every register has a default state. Okay, so if the default state is 0 and you are writing a 0 again to it, that doesn't really make sense, right? So by the way, like many compilers would do that. Like on a higher level of language, they might be trying to set a bit 0 which is already 0, It doesn't make sense, but still it might be trying to do that. So if you code in assembly coding, like assembly language, you won't have to, I mean you can bypass all of it, just write whatever code is required and that's it. And flexibility to write bare minimum code, as in it's kind of the same thing. I don't know why I wrote these management answers, but yeah, okay. Embedded C coding, yeah. So helps bypass unnecessary fail safes. Unnecessary as in, if you, I don't know if you've used with this Atmel AVR Studio, some Atmel Studio, no? You've used? That wasn't Atmel Studio, we still used Arduino IDE, but okay fine. So Atmel Studio is like embedded C compiler for AVR, like the same microcontroller your Arduino uses. Okay, so it comes with its own libraries and its own functions. You can still use those functions and write your code, but again there might be some things that you are not really aware of. Okay, so it's better that you write your own functions and use your own functions. So if you make your own functions and you know what the application is, you will write better functions than what is being provided in the libraries, right? Now better for optimizing algorithms. See, because when you code in assembly, int I equals to 0 is like 3 or 4 statements, 3 maybe, I don't know. Okay, but if you code in C, it's just int I equals 0 or u int I, whatever that is. So you basically save a lot on doing unnecessary work, right? In assembly, coding is like pain. Do you guys started your microcontroller? Yeah, you know how it is, right? So, but yeah, that's how it is. There are trade-offs. So yeah, here you can optimize your algorithm, as in instead of how the logic is implemented, you can improve the logic itself. Got it, right? So you don't really know what the compiler is going to compile it into the final program, but you make sure that yeah, at the program side whatever I have written is well enough. So that's one advantage of C coding, embedded C. And yeah, cross platform uniformity. So okay, suppose you have a code that computes FFT of some, say, some array or something like that. Okay, basically processes something. Okay, if you code it in assembly, you will use instructions that are specific to that platform. When you want to port it to some other platform, you will have to rewrite it again. Instead what you do is code it in C, and because it's embedded C, like common structures like for loop, if, while, those will, you won't have to manipulate them. You can just copy, paste, simple, that's it, done. So that's one advantage of embedded C. And the last one is, yeah, how do you compiler directives, assembler directives?
What are directives?
Yeah, what are directives? Directive is like a directive, like you direct someone to do something. Okay, so like Manan said ki wo all documents ya all camera jo bhi tha, that was a directive from Manan to Tarun. Okay, so compiler directive is we are directing the compiler to do something. Now okay, suppose I have got maybe a push button or something, and whenever I press it, the LED should blink, and whenever I press it again, maybe I don't know, the other LED should blink. Okay, I have got 2 LEDs. So how do you code it? Like in your while loop, you will have if button is pressed, you just invert the flag, and if flag is 1, you just like blink one of the LEDs. If flag is 0, blink the other LED, right? That's how you do it. Now suppose I tell that I want to decide which LED is going to blink at compile time. Like before uploading the code, I know which LED is going to blink. Okay, but I want the flexibility as well that I should be able to change the code like there itself, right? So what you do is like comment an entire section of code which blinks one LED and then decomment the other section, right? Which is kind of lame. So what you do is you like you write a code which has like both of the LEDs blinking, like the code for both of them. But then there are something called compiler directives that you can use. It's like just like if statements. Okay, so these statements will be kind of executed on compile time. How do I tell?
I think they'll be learning it in FP.
Yeah, they'll be learning, I know.
What statement exactly? I don't know.
Okay, So suppose if you open up any Arduino library, there will be something called hash if, not if, hash if, and then hash define is a compiler directive, dude. So what you do there is basically ask the compiler that wherever you find hash, like when you say hash define pi equals 3.14, wherever you find pi, replace it by 3.14. Okay, so you can have hash define or hash if and define something underscore, like if this is defined, use this part of the code, like compile this part of the code and leave the rest part of the code, and if it's not there, compile totally different part of the code. So what it's doing is your code is decided on compile time itself, and you're not checking it when the code is running. Okay, because checking like even a single if condition is a lot of redundancy. Okay, if your program is not executing the other part, first it adds to memory, second it's adding to lot of redundancies, because it's going to check again, like if I want to blink the first LED, and if it's yes, yeah, I'm going to blink it. But then because we are not going to change it once you upload it, there's no point having an if condition, right? So what you do is you just tell the compiler that if I define some variable in the code as this, you compile only this part of the code. No, I didn't do anything. Oh,
Dude, that is frozen on this screen.
okay.
No, the camera on the screen. The camera movie.
Where is it?
Dude, I think I can actually control it from there. It's on
Yeah,
internet, no?
yeah, he can control it from.
It's on internet, right?
Yeah, I know.
Internet of this.
No, NITK.
I think he's on the
I don't know.
Good. I have a question about the compiler itself.
Yeah.
So basically, for the if statement, like suppose if something has to be there, right?
Yeah.
But something has to be defined in the hash defined part, right?
Yeah, it's like you have like hash define hash if something, then you have void blink. Okay, a program that blinks it. Okay, and then hash else, you have another void blink. So they are basically same. Like the function call is same.
No, I'm saying the condition is there, right? I'm asking
Yeah.
The condition, can you put it using some new variable, or we have to define this variable beforehand?
You'll have to define it beforehand.
Using hash define.
Yeah, using hash define. No. It's not like int I equals 0. No, it'll still be a compiler directive.
Yeah.
Because compiler is like, I am going to take care of all this, and your final code will not contain any trace that this was happening. Okay, so if you read the code of the microcontroller, you may not know how many hash defines or how many hash if conditions are there to get the final code, something like that.
So, but in the end, those hash defines, we can't change it during the code.
Yeah, during the code you won't change it. It's just like, so like if you use Arduino, which I guess most of you use, you won't really know like okay, fine. There's Arduino Uno, there's Arduino Mega, there's Nano, Pro Mini, Micro, Zero, whatnot. Okay, but still you still use digital write something. Same function for all the platforms, and still you don't include any other library as such, right? There's just void setup and loop. So how does the compiler know that like I'm going to compile it for this? So whenever you change your board settings, it's that those board settings that are directing the compiler that use this wala digital write. Okay, don't use digital write for Arduino Zero when you are programming Uno, something like that. Okay, any more doubts? No? Logical exploits. Modular nature of digital arithmetic. Okay, so suppose I give you a problem, DAC, digital to analog convert. It's like you give an 8-bit value and corresponding to that you'll get a analog value, like from 0 volt to 5 volt you'll get an analog voltage. Okay, so I want you to output a sine wave which has like 200 samples, which at least has 200 samples. Okay, and it should be as fast as you can go. Okay, so this is the problem statement. Now what one would do is something like this. Okay, what's the spelling of layman? No, is it LAY or LEY? Because I couldn't check. A. Okay, fine. So this is layman's code. Now what he has done is, because the minimum sample is 200 and he wants maximum frequency, he's like, okay, I'll output only 200 samples, that's it, and then loop back again. So these are values of sine wave on 200 different points. It's like you are able to follow along. Yeah. So yeah, 200 values of 255 sine phi. This 255 is because 8 bits. Just keep that in mind, okay? Because 8 bits is 2 to the power 8 minus 1 is 255 over one single period, okay? Then you, that is some 8 bit unsigned integer. Then what you do is DAC register sample of I. Basically in while loop I am incrementing I plus plus, like incrementing I, and then for that sample value I am outputting to DAC, okay? That, but and then if I is greater than 199, make it 0. What do you say? Standard way of coding in C, right? Like whenever the output variable is more than the limit, set it back to 0 so that it will keep on looping. Now, yeah, so to output sine wave, okay, this see, so this takes 1 clock cycle, this takes 1 clock cycle, this is 1 clock cycle, this takes 3 clock cycles because there's if condition and an assignment, okay, and get back from this point again to the while loop, okay. That is, so if you use these clock cycles, you'll get like for one complete sine wave, to output one complete sine wave, it will take into 200 plus 3, which is like 803 clock cycles, because see, these statements won't be executed again and again, like this one, I equals to 0, fine. It's only when it's greater than 199, it will be executed, right? So that plus 3, and because you have 200 samples and 1, 2, 3 and 4 clock cycles, these 4, so you have got 4 to the 800 plus 3, so it will take 803 clock cycles to output one complete sine wave. Let's see how can we optimize this. Okay. Yeah, smart guys code. It's already smarter because it's like just lesser lines, right? So what he has done, 256 values, if I, okay, using 200, this is using more values, okay. So instead, like that guy had to loop 200 times in order to output 256 times to output the same sine wave. If you see, this is like a uint underscore 8 variable, right? It's an 8 variable. So what happens when you add 1 to 0, 1, 1, 1, 1, 1, 1, 1? Yeah, it resets to 0, 0, 0, 0, right? Here there's no condition on I. So what's happening is, I will keep on incrementing until it reaches 255, which is like the last sample. And after that it increments and resets back to 0. So there's no need for the if condition, which was taking more clock cycles. Okay, so you have got just like 3. This code is going to take 3 into 256 samples, like 768 clock cycles, and 803 clock cycles, right? So you have more samples per cycle, so it's like a precise sine wave, and the clock cycles is less, so you can generate higher frequency sine waves. Okay, so this is what when I said module in digital arithmetic, it's like your okay, in this case it's 8 bit, right? Yeah, so exactly like a clock, so you don't have to explicitly tell it to go back to 12 and 1, no, it does it on itself, right? So you use that logic so that all this comparing thing and the overhead which is to output sample, it gets chucked off, right? So last point is, logically there are some operations which are very easy, like addition, subtraction and left shift, right shift, and some which are difficult like division, okay. So is really a time killer operation. You have multipliers on board nowadays, but dividers, no, we don't really have division like implement. So try to avoid divisions, okay. I don't know if, yeah, you must have learned that left shifting is multiplication by 2 and is division by 2, okay. So is right shifting always division by 2? If I right, yeah, I mean, yeah, always for sine, No, what if you know arithmetic?
If you do ASR, yeah, but LSR won't.
Okay.
I was trying to say this. If I have 3 and if I have 2, I right shift by 1,
Hmm.
it does it.
Hmm.
I still get 1.
No.
It's the step.
No. Thing is, okay, fine. 3 right shifted by one place gives me 1. I am fine with that. Okay, I am fine with round off errors because it is 1.5 which I cannot represent. I can represent 1. I am fine with that. But is it still division? See, basically when you do 3 right shifted by 1, like you are basically getting the quotient. Yeah, you are not like caring about the remainder. Fine, but then is it always the quotient that you get? Is my question. It's something like we take for granted. Like try right shifting -1. Do you get 0? Yeah.
You get the highest possible. Highest possible.
I am talking arithmetic right shifting.
Yes.
You'll get -1. You divided -1, you got back -1. So for arithmetic right shifting, the minimum you can get from -128 to -1. You won't get 0 again. Okay. So these are like some things you might never, until unless you code it on embedded C. Because Arduino and all are smart enough, they'll have some functions that will take care of that -1. It'll get it back to 0. But then that's again extra overhead, right? So yeah, division is time killer, don't use it. Architectural exploits. Okay, possibility of parallelism. Do you think parallelism is possible in Arduino?
What is parallelism?
Parallelism is like doing two things like simultaneously, like eating a banana while you're writing a record or something.
So like 2 commands at the same time.
Yeah. No. Exactly. At hardware level in Arduino you cannot really have two like shouldn't say instructions, but two things going on simultaneously. But then at software end, like single core processors still multitask. Yeah, I mean at hardware level they are not supposed to do tasks in parallel, but still you can do that in software. So you can do software parallelism. Okay, suppose you have a digital system that takes in some input from, let's say, analog read and process it and give some output. Okay, fine, and it's single core. So there's nothing like one core is doing something else and the other core is doing something else. You have got just one core, right? So what you do is like do both the tasks simultaneously with kind of time division multiplexing. Like for some time do this task, then for rest of the time do the other task, and keep on switching between them. And they have its own advantages. If you do real time processing, it's like getting the sample, processing, giving the output. Now while you're processing and giving the output, you're not taking any input, right? So you might miss something. You don't want that. So what you do is take an input, process something, again go for an input, process the same thing, then like keep on jumping between stuff. Okay, so it's not exactly parallelism at hardware level, but you are kind of donate like let's say like that you have 1 millisecond of length of say time. One code says that for the previous millisecond I'll just take the inputs, next millisecond I'll process, third millisecond I'll give the output. Software parallelism says that in the 1 millisecond, 1/3 millisecond I'll take input, 1/3 I'll process, and the rest 1/3 I'll output. Okay. So those really help. Okay, like especially in when you take samples in real time, you don't want to drop any information, right? So this is like one way to achieve that. Yeah, shift and add. It's like I don't know. It isn't exactly parallelism, but you can code in a smart way that your what do you say? Operations are okay. I don't know if you have come across the standard question like multiply by 5 without using multiplier, right? So what do? You shift and add. Apart from that being cost effective, there are like many processors have the facility to shift and add in the same cycle. Okay, so it's like you're doing kind of doing two operations in a single cycle. So this is like a very primitive kind of parallelism that you'll find in okay, let's say very general purpose microcontrollers. That's the more humble word for saying like less powerful or crappy microcontrollers. Pipeline exploits. Okay, you know pipeline, right? You don't know? You know manufacturing pipeline, right? Yeah, it's similar. So holy grail of microcontrollers or microprocessors. So I don't know, like if you had attended Tarun's talk, he said something about out of order execution. So okay, like suppose there's something which is you need a variable which is current in this part. Okay, like okay, fine. Like these bars that you see, kind of what do you say? Like different work is going on in different sections. Okay, so,
Transmission part one.
yeah, it's like there's your chassis, there's the body, there's the wheels, and there's the engine. Oh wait, first you then wheels, right? Okay, and then so suppose somewhere here or somewhere here, because ALU is here, this guy wants a data which is over here, like which is still written to be in the memory. Okay, and you want it. The code, this guy, this data. What the okay, data is here. This guy cannot. So instead of executing that, it won't do anything. Like I'll sit idle. I'll just have a no op, like no p. So you don't want that, right? It's like a clock cycle, which isn't much if you have a 16. It's a clock cycle, and you want to save it. So what you will do is instead request this completely out of the world. Okay, so does this the data that you want will be returned to your data memory or whatever, and now it's available. So now you can like use that whatever instruction that you wanted to execute, and because it's already available, there's no operation instruction as such. So you kind of saved that clock cycle. Okay, so yeah. Got statement 1, statement 2 which depends on 1, okay, and then statement 3 which do as told in statement 1. This is like the compiler compiling it, so it'll compiler or assembler, it'll compile it like this, do as told in statement 1, wait for statement 2 pop out of the pipeline. So once you have the variable like with you, then do as told in 2 and do as told in 3. Now instead of doing that, okay, yeah, what you do is have statement 1, then instead of 2 execute statement 3. So while statement 3 is getting executed, statement 1 will pop out of the pipeline. So you have the data now. Once that is available, you can execute statement 2, then it won't have basically a no operation statement. Okay, so that's like you the clock cycle. Yeah,
Basically, every statement takes one clock cycle.
not every statement takes, but let's assume for simplicity where there are statements that can take up to 4 clock cycles, like single assembly statements that can take up to 4 clock cycles. So that brings me to the next point, knowledge of platform that you're working on. So it's always good to know what you have at your hand and what is not there for your entertainment. So this right here is like the first of data sheet of your AVR family. It's a general data sheet, like this is kind of valid for Arduinos as well. So what all do we need out of these many lines? Okay, first thing is 8-bit microcontroller. So 8-bit means like the for simplicity call it that the what do you say, the data that your ALU can work with is like max is 8-bit, cannot go beyond that. So for every operation you'll get like 8 bits is max it can put through. Other thing is 32 general purpose working registers. So in the lab you'll have like 15, whatever controller you use, it has 15 registers. This is like 32 general purpose registers. Like your program is working with fewer variables, don't really go to fetch data from RAM or from data memory. Okay, just store it there in the general purpose registers, especially if you are coding in assembly, and get it from there. Okay, so no need for this LDR and whatever stuff you do to fetch it out of the memory and then do something. If you have 32 registers, and even if 24 are available, A plus B equals C is kind of can be done in the register itself, right? So because register access is faster, you'll save more clock cycles there. Okay, 2 cycle multiplier. Now this kind of not so, but okay, because most microcontrollers nowadays come with multiplier, so you won't really need to worry about this. You can give A equals B star C or something like that. But again, like if you have two 8-bit numbers that you are multiplying, the result is 16-bit, right? And since your ALU can only work with 8 bits, it will take 2 clock cycles to break that 16 into 8-bit and then store. So you might want to consider that as well. And then peripherals. Peripherals are important because the last point that I spoke was free the ALU, right? Peripherals are kind of helpful when you want to free the ALU, like I++. Instead of doing that in normal code, you can do that on the timer side. Like have a timer set to like count once every like for a complete iteration, it will count 1, something like that. So you have a for loop, while loop, and for every execution of while loop, like the completion of while loop, your timer increments by 1. So don't have to increment, do this I++ thing in what do you say, in your code. So ALU is kind of free for that 1 clock cycle. And then PWM channels, 8-bit ADC. These are more on application side. They don't have anything to do with optimization. But again, it's like 10-bit ADC with an 8-bit microcontroller. If you take the 10-bit value, again incur cycles or more number of clock cycles to process the same data. So if you can maybe cut some cost of with this thing, the accuracy, or what do you call it, precision. If you don't really require precision, don't use the 10-bit, use only 8 bits. What's wrong if you want to save clock cycles? Okay. Now as I told, 8-bit, 32-bit or 16-bit. If you are using an 8-bit microcontroller, don't really go for like a float, or don't write double, because they are like kind of heavy data types. It's not easy for smaller microcontrollers to handle. So just know what are you working with. Okay, fixed point and floating point, as I told, don't do like float or float underscore 32. It's like 32 bits is like you'll need 4 bytes to store just one operation, and because your ALU is 8-bit, it'll take 4 clock cycles to do like just to add 2 numbers, maybe more than that, who knows. So yeah, as a multiplier of course it has, so no need. Use whatever is needed. Okay, so suppose in that example I had used like uint 8 underscore t, right? I could as well use int I equals 0, but then integer is translated into 16-bit integer, and the value is going from 0 to 255, using the entire width integer, right? Don't use an integer, use a data type which is smaller, compact, which is implemented, like all the operations are implemented in a faster way, so that you are using whatever you have defined to the fullest, and you're saving clock cycles basically. Arithmetic of 16-bit integer on, yeah. So even this will be a question, like you program to 4-bit numbers, right? So what do? Take or whatever, then add the next 2-bit 32-bit numbers. Carry was there from the last one, add that as well. It's not really best thing to do, right? So instead of having 64-bit integer arithmetic, try to use 32-bit. Like, what's wrong? Oh, not 32, 16. Causes unnecessary overhead. Yeah.
I didn't understand the previous one. What do you mean by
Software as in, so what you will do if you had two 16-bit integers, what you will do is, okay. Okay. Yeah, it's fine, it's fine.
Okay, so
16-bit integer is like, bits, right? 0 1.
yeah,
16-bit is like 16, like, yeah, 16 spaces.
in,
Yeah, zeros and ones, bits.
2 is basically 2 is equal to 1 0 only, right?
Yeah.
So how will I replace 2 with 16-bit and
1 0, but for the rest of the 8 bits you'll write zeros. Like, all zeros, 1 0.
I can store a larger value with 16-bit.
Yeah, but if you are using from 0 to 10, doesn't really make sense to have like a value which is from, yeah, all 8, or in this case, like if you have an 8-bit CPU means you can use 8-bit, like no issues with that, but 16-bit doesn't make sense. So add them up. What the compiler will do is, this is one instruction, add. Then store the carry, which is implicit, so it's not an overhead. Then add these two along with carry. So this ADDC or something. Yeah. So what happened now is, it was able to get perform 16-bit addition, but then your clock cycles were more. So it's like, if it had been a 16-bit CPU, it would do that like in just one clock cycle, but now it will have to, yeah. So but in software, that is what I mean, like in software as in, you'll have more instructions to do the same thing. Yeah. If you have two 8-bit addition, like one 8-bit addition,
whenever you switch to software, I don't understand it.
software as in, your code will have to do that. See, when you do int a equals something, int b equals something,
You have to write the store carry and then you use ADC. That you mean that.
no, I mean, see, it's suppose that I am doing all of that in C coding. Okay. So what will you do in C coding? Int a comma b comma c, a equals something, b equals something, c equals a plus b. When it gets compiled, it will be like, first take
First to,
yeah,
be 8 bits,
add them up, yeah,
then use that carry
yeah,
the
and then,
8 bits.
yeah. So basically, what you see in C code as just one line of code gets translated to 2 assembly lines. Okay, but when you use like the length which the the ALU is supposed to handle, and that time, yeah, it will be like just one clock cycles, right? So it's like, don't be like spoiled brat or something when you want to declare variables as such. Okay, don't use ints and, yeah.
I should take care while writing the C code itself.
Yeah, so whenever you write the code, just because you being programmer know that it's going to execute like max of 200 times, no need for an int. Use an 8-bit unsigned integer, something like that.
Basically what you're saying is, we have the number small,
Yeah, use a small, yeah,
8 or 8,
yeah, exactly.
that is if you know the value is not going to go higher than
Yeah,
256 or
okay. Now peripherals at hand. Okay, this is like something, again, like the timer example. That is just one way to kind of save the clock cycles. There's something called DMA. I'll come to it at a later stage of time. So just for now, peripherals can be used to kind of optimize your code. Okay, this is like an example when you want to implement So you don't try to avoid. Okay. Algorithm optimization, bit manipulation. Okay. Swapping two numbers. Do you know how to swap two numbers using bit manipulation? Yeah, exactly. So how would that be? Yes, exactly. So damn, someone has done some homework. Fine. Yeah. So that's yeah. I know. Still. So it's like bit manipulations are kind of the most basic operation that you can do in any platform. Okay. So if any operation which is complex boils down to bit manipulation, use bit manipulation. Okay. So in the last code there were 256 sample outputs. Suppose I want them to be 64. What would I do? The output variable is still like 0 to 255, right? 8 bit is 0 to 255. I want it to limit it to 0 to 63. Let's say 63. Okay. So what would I do? Remember that like platforms, they can do like a logical operation and an addition and subtraction in a single cycle. So what you can do is have a bit mask. So it's like yeah. So this is my register. It's a bad register, but okay. I want to limit my what do you say, counts from 0 to 63. Okay. So 0 to 63 is 0 is all zeros and 63 is yeah. Fine. So what I would do is I would make a bit mask. Let's say bit mask equals 0 0 and all of them ones. Okay. Yeah. So now thing which if I AND it with any number will knock off these two bits. These two bits will become 0 and these being 1 it will be like as it is, right? So whenever I like instead of doing I plus plus and if conditions whatever, what I would do is I equals I plus 1 and it with my bit mask. Fine. So what it will do is it will count normally till this point, and after that like when you add 1 this bit will become 1 and these will become 0. Fine. And when you AND it with the bit mask this bit will be knocked off. So again you end up with 0. Fine. So this thing when you go for any filter design or stuff, you would here power of 2, like 2 point per count, easier to set back to 0. Okay, so where's my pen? So suppose I was doing right, yeah, all right.
And then, so the addition, do they take place in the same cycle?
No, most of the microcontrollers don't, but the I don't know the STM series have the possibility like they can do a logical operation and an arithmetic operation simultaneously. So again it depends on this.
Basically, in this, like you have the number 63.
Yeah,
So when it becomes 64, it's supposed to become 0.
yeah,
So instead of doing plus 1 and setting it to
0
you do it, you add 1 and then you add
and it with this bit mask. So it basically sets all the higher bits to 0. Yeah. Yeah. Oh, that's my next point. Sorry. That was my next point. Using circular arrays for buffering data. So this I and thing can not only be used for looping but for storing values. Suppose you need like 63 values or 64 values, kind of you do a convolution, okay, you are doing a convolution. So you need like 64 values, and when a new value arises you want to pop out the old value, right? So what you can do is you can implement what do you call it, एक होता है stack, दूसरा होता है queue. You can make a queue that okay, this is the queue, this is the start, push in, pop out, fine. Problem is when you do that your entire queue is kind of moving in the memory, right? But then memory has a limit, like it starts somewhere, it ends somewhere, so you cannot have a queue. So what you would do is use circular addressing. So what happens is like okay, first value here, second here, third, fourth, fifth, sixth, seventh, eighth, and then once a new value arises this has to be popped out, right? So you write the new value over here, okay. So that is like you won't have to yeah, exactly, you won't have to shift the values. It's like or what you could have done is copy this value to the next one, this to the next one, this to the next one, then you got some space. Instead of doing that, the value write the last value, okay. Now when you process this data you'll have to use this bit mask and stuff, you'll have to use circular addressing, okay. Huh? Okay. Okay, so here is your buffer, say array of 8, okay, and like from the start of the program you are going to store some values in them, okay. So what will happen is first value, second value, okay, eighth value. Now what if you want to like enter more values, okay, because the stream of data is continuously coming in, right? So either like pop this guy out, add one more, write a value, but then the memory issue, so we cannot do that. So what, copy second guy here, third guy here, so on, and then this is empty, so here you can write the ninth value, but this is time consuming because copying so many values, like shifting all of them, doesn't really make sense when the same values are going to be used. So what you do is instead of manipulating the like the physical number in the physical memory, you manipulate the address itself. So what you do is the ninth value, instead of writing over here, you write it on first value, okay. So you have 9, 2, 3, 4, 5, 6, 7, 8, fine. So now when you use this kind of addressing you can do this bit mask thing that I told over here to address circular buffer, because now like if you want to address 63rd value, which is stored again in 8-bit thing, right? So 63 is not like from the base you go to 63rd memory, no. From base you go 63 mod 8 because it's an 8. So no mod. So 3 mod 8 is 7. From just go to 7. This easier. Like changing is effect than copying everything to previous. Yeah. 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 To this end will help. Okay. So basically, okay, what is convolution is like you'll have an index that will run from here to here. Okay. Fine. So your 0th position. What's this? 7th position. Fine. Like it's sum of products, whatever that is. So you'll have some coefficients, multiply add, and you'll get one output. Fine. Now you want another input to be written over there. So what you do is use, but okay. Performing. So your last multiplication will take with the 0th address, kind of. Fine. The next one on second. Okay, that's why it's called circular address. Oh. Yeah, I mean if it's linear array, okay. So how would you store the values? Like if it's linear, you'd want the second data to be at this position. Exactly. So copy this guy over here. If second to be here, third should be here. So you are like kind of basically having all the data copied from one memory location to the other location. And doesn't really make sense, right? Because the data is same. So instead of like copying all the data, give an offset to your initial address itself. Earlier the address was starting from 0 to start for convolution. Give it 1 and circularly buffer it. So like after 7, it will loop back to 9th position, multiply and add, something like that. I'll send you the code. No, I've written the code. It's not that I've copied it from somewhere, but it's beautiful. The code is really. It's not something that can be discussed on a group. At least I don't want to be called a spammer on yet another group. So, balancing speed and memory. Okay. Classic Nokia game. Fine. I'll have to again. So I hope most of you have played the Nokia game, that snake game. You eat some random stuff, spiders and all, and you keep on increasing in length. So let's see, you have array, right? So whenever I write a 1, that box is black. Fine. So okay, we started the game. What's a small snake, like length of use your keypad, give some input, it will start moving, it will eat the food, and then its length will increase. Okay, now that's how your game looks to you. Okay, there are two different implementations for the same thing. Fine. So first thing is, you have a 16 cross 16 matrix. Fine. Every position represents the state of that pixel. Okay, so if it's 0, it's white. Okay, so what you do is, when you want the snake to move from this, from this position to this position, it will be somewhere like 1 1 1. You just clear and set. So it has moved, right? Now so there's one part of the code that is taking care of this matrix manipulation. The other part of the code is doing this, writing it to the screen. Okay, there's some kind of a parallelism. It's more like jumping between the tasks, but let's say that it's parallelism. So here a 16 all these are zeros. Okay, you know, most of them are zeros. There's no point 16 cross 16. What's the time now? It's stuck. Vashishta, your laptop is no. Oh yeah, nice. होने में ही है. Yep. Okay. Fine. So okay. फटाफट. वो टीवी पे है. हाँ. Oh, I was there. So you just see there. It's like taking a lot of memory, right? You don't want that. So what you do is, instead of having 16 cross 16 array, have just two variables. Okay, 2 or 3 or whatever variables to store head, tail. That's it. Okay. Of course, like For different pixels you will have like the entire length, but instead of storing the entire array, just store the x and y coordinates of whatever pixels are 1. Okay. So let's assume the player is novice and won't last long. He maybe made a snake of length 10, like a lot less memory compared to the 16 cross 6. X and y values of just 10 variables. Okay. So okay, that you have like 2 faster. Why? Because you just need to know what is the direction and manipulate individual numbers in the array, right? But that one is more memory efficient. Okay. In that case, again you have x and y coordinates. Depending on the input, you change on the x coordinate. If you look at the algorithm, simple, that one is complex. But if you look memory wise, this one is like more memory consuming and is like kind of light on memory. So that's what when I say like balance memory and speed, what do you want? What is your priority? If you have loads of memory, then it's like you utilize all that memory and have a higher speed of computation. Fine. The next thing is free the ALU. Okay. These I'll just quickly go through. Don't let the ALU do useless stuff like I++ and moving data around peripherals, like getting the register to a register. That can be done by some other peripheral instead of your ALU. Okay. So don't let the ALU do all that stuff. The other thing is use interrupts, because asking the ALU to wait for something is useless. Don't do that. Use interrupts to kind of interrupt the ALU, let it do whatever the interrupt is asking it to do, and then get back to your main program. So that way you're not wasting clock cycles, nothing, sitting idle. Okay. So that is the other method that you would want to keep in mind, that if you have like different tasks that are asynchronously happening, use interrupts. Okay. Use peripherals, timer example for this thing, incrementing counters and stuff. SPI peripherals to talk to shift registers. Okay. Do Google this thing, it's like very interesting. If you know, in Tech Nights we had that board thing, right, 32 cross 16 matrix, it used SPI. The same thing can be done using GPI as compared to this. 32 cross 16 we banaya matrix. Yeah, we had a this, but then we didn't use digital IO for clock and all. No, we used the SPI peripheral. Give it the data, it will do everything for you. Meanwhile, you can do something which is more meaningful, like data from Wi-Fi, something like that. Okay. Timers to generate random numbers. Oh, this is like my own recipe. So in that snake game, if you want to put a food somewhere, it should be random, right? How do you generate random? Microcontroller. Need an analog value, but again, it's time kind of not really the best way to generate random numbers. What you can do is have a timer running at a very high speed. Okay, and whenever you want a random number, just read it, because you don't really know like at what point you'll need a random number or what exactly will be the, it's random to you, right? So this is like kind of using your peripherals for what they are not meant to be, like they were never meant to generate random numbers. You can use them, right? Okay, DMA to move data between memory. So DMA is a peripheral that you can configure beforehand to kind of exchange data. So if you want some data to come from ADC register to some of your general purpose register, configure the DMA to do that. So now processor is like hands free, it can do something else. DMA is going to take care of all the data movements. Okay, so peripherals like DMA are like very kind of important, like if you really want something which is high speed and the throughput is too much, like something. Okay, that's it. Any doubts? Yeah.
You have time?
Yeah, we have 5 minutes.
Two questions.
Yeah.
With that byte, the sampling thing which you give, right?
Mm-hmm.
Byte int. I don't know syntax. What does that mean?
Byte int is in it's just 8-bit number, like it's just 8-bit number. Byte is like,
So byte is 8 bits, right?
yeah.
When you byte int is equal to 6. What does that mean?
Did I write byte int? Byte A.
Yeah, some int, like you write.
Yeah, so it's like it's like I want a byte data type which is like 8 bits, and I name it A, and I want to store 6 in it.
So it will be like 1, 1, 0, something like that.
Yeah. Even when you do int A equals something, it is stored again as 0, 0, 1, 1, whatever that is.
But why do you write byte then?
Byte is because it's supported in Arduino, and when you say byte, explicitly converted into 8 bit. If you write int, it will be explicitly converted into 16 bit. Yeah. Okay.
Are they supposed to be in sentence in this slide?
Are they supposed to be?
Points in this slide?
Yeah.
This thing.
No, because I want to.
So this embedded C, right?
Yeah.
I didn't understand what exactly that's basically C language.
Yeah. See, it's like your Arduino is based on embedded C. Okay, so embedded C, Arduino.
Okay.
So instead of going like using Arduino, which will have some redundancies, go directly to embedded C. Okay. Yeah. So that will optimize your code to like the last example, like the at the very beginning we had some 4 times gain in memory.
Yeah.
4 times less memory was used. So
Okay. So how do I write an embedded C? I can write.
you can use an Arduino ID. Just don't use analog read.
Oh, it's just analog.
Yeah, don't use analog read. Use ADCSRA equals something, which is
What we just block.
yeah. You read my article. Article. IEEE article.
TechNet में बैठा के पढ़ रहा था.
आराम से कंट्रोल.
पहले बात तो बोला
So hyper हो रहा है अब. I know. I'll conclude. Anything?
We'll play your video.
Yeah.
Play your video.
हाँ डांस वाला. TechNet room dance.
एनीवेज मेरा कोड दिखा चुके यार बेइज्जती हो गई. चलिए लगा दीजिए.
क्या? नहीं.
बहुत
It's it.
हमारे पास टाइम है.
Done?